Hello. Thanks for joining. Today we're going to be doing part 2 of the PICO-8 game dev stream where we're going to learn how to make PICO-8 games. Last time we got to a point where we had a little sprite that we were able to move around the screen. We learned how to draw stuff. We learned how to make sounds. Learned how to play sounds. And we made a very simple just kind of showcase of all the things we learned. Today I think what I want to do is I want to clean up what we wrote yesterday. I want to go over hit detection, do all the mathy stuff, because hit detection and collision detection are a super important part of making a video game. And then do some other cool stuff. But those are going to be the two big ones. So I just loaded up game-1, which is the game we worked on. And if I type, run, we can run our game. And last time we made a little pumpkin, a red pumpkin named Henrietta that can move around the screen. I'm controlling it with the arrow keys right now. And if you press Z, it makes a little sound. And if I wanted to open up this file in Sublime Text, my code editor of choice, I just type folder, and I can drag it into Sublime. So we have a pumpkin object that we're creating when the game starts. And it has an X, a Y, and a color, and a name. And in the underscore update function, 30 times a second, we move our pumpkin across the screen based on which buttons are being pressed. So if the 1 button is being held down, which is the right arrow key, then we'll move the pumpkin's X coordinate up, which effectively moves it right. Same thing for moving left, moving down, and moving up. If the 4 button is pressed, which corresponds to the Z key on my keyboard, then we'll play a little sound effect. Yay. And then we have all this drawing code. We're drawing this blue rectangle, this pink circle, this little yellow pixel down here, and this green square up here. And then we're also drawing our pumpkin, which is a little pumpkin sprite. If we go into the sprite sheet editor, you can see I'm drawing sprite 4, which is the 4 over here. And I'm drawing it at the pumpkin's X and Y coordinate. It's red because we're calling this pal function, which stands for palette, where we're changing 9, our orange color, to the pumpkin's color, which we set to 8, which is red. So that's why instead of orange, it's showing up as red. And we're printing out the pumpkin's name right above the pumpkin in the color 7, which is white. And I want to start by doing some cleanup. So let's start by, I'm gonna save this as a new file, game-2. And then I'm gonna load up game-2. And I'm gonna actually drag that file into Sublime so we can work on that. So now we have a new file for what we're going to be working on today. So the first thing is we have a bunch of comments and extraneous code that we don't need. So let's do this. Let's get rid of these comments. Let's get rid of these. So we have all the code that moves our pumpkin. We have a play sound when this is pressed. I think we know what all this does, so I'm just going to get rid of these comments. They're a little busy. We have all this code in the draw function that is drawing this blue rectangle and circle and whatnot, but they don't really do anything. That was just us experimenting with the drawing functions PICO-8 has, so I'm going to get rid of these. Boop. Boop. And boop. Let's do it like this. Clear the screen. The CLS function clears the screen. You can actually pass in a parameter to this. The first argument, you can pass in a color, and then it'll clear the screen to that color. If you don't pass in an argument, it'll assume you're passing in 0, which is what I want. You can see when I run my code now, there's not all the extra junk on the screen. So now our code is a lot simpler. I think let's take out this play the sound stuff. We don't need that. That doesn't matter to us right now. And what I want to do is we have this pumpkin object, and we know how to update the pumpkin, and we know how to draw the pumpkin. But This is maybe a little bit of a tricky way to do this, because if we start adding other stuff to our game, like if we start adding like 50 different things to it, it will be weird to have the data related to each of those objects under init, what needs to happen to update them under update, what needs to happen to draw them under draw. I'd prefer if all of the pumpkin code was sort of consolidated, so if I wanted to edit how the pumpkin works, I could go to one place. Let's say we made a new function, and we called it draw pumpkin. Let's say we passed in an argument p, that is our pumpkin, into that, and then we drew whatever is passed into that. And in this case, it's going to be the exact same code here, but instead of referring to pumpkin, we're just going to refer to p. So I've just created a function, draw pumpkin. It takes one argument, and what it'll do is it will basically draw a sprite at p's coordinates with p's color, with p's name, whatever p happens to be. And what I want to do is, instead of in this underscore draw function, instead of having all this code, I just want to call draw pumpkin and pass it in our pumpkin. Which, let's say, how about we change the variable name of pumpkin? Yes. Let's change it to Henrietta, since that's the name of our pumpkin right now, P. So you can see now we have an object called Henrietta, and in the underscore draw function, we're calling draw underscore pumpkin, and we're passing in Henrietta, which in our draw underscore pumpkin, we're going to refer to whatever is passed in as P, and then we're going to draw it. And if I save this and run it, it works just the same. And if I wanted to just verify that this really is working, I could change 8 to 12, which it should now be blue when I run this again, and our pumpkin's blue. Yes. One step better than this is I said I wanted all my code to be in one place. So let's do this. Let's copy our draw underscore pumpkin function, and let's have Henrietta have a draw function. And let's have it be the exact same stuff. And instead of calling draw underscore pumpkin, which no longer exists, let's say this: Henrietta dot draw Henrietta. Which is a little bit weird that we're doing Henrietta dot draw Henrietta. What we'd like to do is we'd like to not have to pass in Henrietta. We'd like that to just be implicit with the fact that we're calling the draw method Henrietta's draw method. So what we're going to do is, if you do colon instead, it will call this method passing in this object it's called off of as the first argument. You can see it still works. Yes, yes, yes. And up here, instead of P, a common nomenclature is to have this be self. Self. And you can see it even does some syntax highlighting on that. So now, this is getting really good. In my draw method, I just say, hey, Henrietta, just draw yourself. I don't know how to do that. You know how to do that. And then sure enough, Henrietta knows how to draw herself. And actually, let's just change this back to pumpkin, because now there's no more ambiguity. Pumpkin. So now the pumpkin knows how to draw itself. Let's take off the name. Make it simple. Now our pumpkin knows how to draw itself, and better even yet, all of our pumpkin code is in one place. The only thing that's not here is this code relating to moving it. Let's do the exact same thing. Let's call pumpkin :update. And let's give our pumpkin object an update function. And let's just paste that code right in. And similarly, instead of updating a pumpkin, we're going to update self. So now this is really good code because all of the code related to our pumpkin is in one single place. It's right here in init. The pumpkin knows what data it has, it knows how to update itself, it knows how to draw itself. And then all that the underscore update underscore draw functions do is they call pumpkin, now's the time to update yourself, pumpkin, now's the time to draw yourself, and they don't even care what it does under the covers, which is a good separation of concerns. And if I run it, it still works. Still got our pumpkin moving around. Yeah, so this looks good. I want my pumpkin to be orange because it looks better that way. Or maybe we should just take away the concept of color. Let's just stick with orange for now. Now let's get into the meat of it. Let's do hit detection. So let's make something for our pumpkin to do. Let's make a classic thing. Let's make a coin. Every game needs coins for our pumpkin to collect. I just drew a little coin. It's in sprite number 7. Now we can do a similar thing where let's say I have a coin. And let's create a coin in the exact same way. Let's have our coin have an X position and a Y position. This will be X equals 80 is 80 pixels from the left, which is mostly towards the right hand side of the screen. Y 100 is mostly towards the bottom of the screen. We want to do the same thing where we have an update function and a draw function. And in here, I'm going to do the same thing where I update my coin and I draw my coin to the screen. Great. And I know what drawing my coin will look like. It's just going to be drawing this coin sprite that I just made. Self that X, self that Y. What do I want to do to update my coin every frame? I don't think it does anything. It's just a coin. It sits there. So, unexpected syntax. We got an error on line 37. That's going to... That refers to this. Per 7. Oh, we forgot to add these parameters here. Self. There you go. My coin's down here. I can't collect it yet, which feels bad. I actually did like when my pumpkin was moving a little bit faster, so let's do this. Let's do this. Move speed equals 2. And then instead of changing this by 1, we'll change it by self.move speed. And now my pumpkin should be twice as fast. And now if I wanted to control how fast the pumpkin is, I can just change this variable. Haha. Woo! Great. 2. Let's work on hit detection. There's lots of ways to do hit detection. Let me open up ASCPrite. This is my favorite sprite editor. Let's say you had 2 goalposts and you wanted to test to see if this little pink ball was between those 2 goalposts. One way to do that would be these goalposts are probably represented as X values, so it's going horizontally, so it's like it's going along the X axis. Let's say that this left goalpost is at X equals 20. Well, yeah. And then this X goalpost is at X equals, let's say, 50. So one way to see if this pink ball was between these goalposts, and I just mean in the X axis. So imagine it's moving along this line, and we want to see if it's on this part of the line, is to check this dot's X value and see if it's between these 2 numbers. So if the pink dot's X value is above the right goalpost, then we know that it's not between them. It's gone past it. If it's below the left goalposts, then we know it's also not within those goalposts. But if its X value is between the 2 of them, 40, then the point must be between the 2 goalposts. What's cool about this is we can extend the same concept into 2D collision detection of, let's say we had Let's say we have these goalposts over here and these goalposts over here. Let's say we're checking to see if simultaneously if this little pink dot was between any of the goalposts. So if the pink dot was right here, then it would be between these green ones in the y-axis. So now you can kind of visualize as I move the pink dot whether or not it's between these two lines, and the way we can do that mathematically is this is the y value we're looking at of the pink dot, and right now let's say the y is at y equals 25 or something like that, which we can see is between, this number is between 20 and 50, and this dot is also between the two goalposts here. And if we were to move it outside of it, then this would represent something like y equals 15. And we can see that the y value is outside of the 2050 goalpost, and the dot is also outside of this area here. And similarly over here, we can see if the pink dot is between these two blue goalposts here by looking at the x value. And if we do this simultaneously and we try to figure out, is this pink dot between these green and these blue goalposts at the same time, like let's say it was right here, if you kind of just take away these, this becomes a way of checking to see if a point lies within a rectangle. So that's kind of like how we're going to start hit detection. And there's many different types of hit detection. This is the one we're going to do for right now, just to kind of get a hang of it because I think it's the simplest one. But let's do this. We need a bounding box around the pumpkin. So I want to draw a rectangle around the function from its x coordinate to somewhere. It depends on the width and height we want to set on this pumpkin, so let's do that. I think a width of 8 and a height of 8 would make sense because that's how big a standard PICO-8 sprite is. So let's do self.width, self.y plus self.height. Let's do 7, which is white. Let's see what that looks like. So now we're drawing a little bounding box around the pumpkin. And you can see if I change these width and height parameters, the bounding box gets bigger. You'll notice also that the pumpkin is in the upper left side of the bounding box. So basically the x and y value of the pumpkin represent the position of the upper left corner of the pumpkin. And that's why if I make the white width and height too big, it grows from the upper left corner. But 8 looked right to me. So now we're drawing a bounding box around the pumpkin. Let's draw the set self.x, self.y, 7. Let's draw a little dot where the coin is. And you can see here especially, I'm drawing a dot where the coin is, but it's actually misleading. The location that the coin is drawn is sort of offset from where the coin is actually represented in the code. And that's again because though the coin is at a certain x and y position, when I draw its sprite there, it's setting at the upper left position of its sprite to that point. So if I wanted to correct for that and I wanted the coin to be displayed right where the coin is in the code, I could just subtract a little bit from where it's being drawn. Let's get some more contrast. And now you can see the coin sprite more properly represents where the coin actually is. There we go. So now, let's say is vertically aligned equals false. Let's print is vertically aligned. Interesting. Oh, self dot is vertically aligned. False. So now print just prints some text to the screen. The text I'm printing is a Boolean value, Boolean being a value that's either true or false, and just printing that next to the pumpkin. And what I want to do is every update frame, I want to set self that is vertically aligned to true if it's vertically aligned with the coin or false otherwise. And that way we can kind of get a visual representation of seeing when it thinks it's vertically aligned with the coin. So we have the coin's x value, which is coin.x, and we have local left equals self.x, local right equals self.x plus self.width, So I'm getting the left and the right value of the pumpkin. I told you before that the X and Y value of the pumpkin represent the upper left corner of the pumpkin, the position of the upper left corner, which means that the X value of the pumpkin must be the left side of the pumpkin, and the right side of the pumpkin would be the left side plus the width of the pumpkin, and that gets you to the right side. So I have right here variables for the left and right side of the pumpkin. Check to see if the pumpkin is aligned with the coin. And all I need to do is if left is less than coin.x and coin.x is less than right, then self that is vertically aligned equals true. Else self that is vertically aligned equals false. So it's really simple. We're just checking to see if coin.x is between the left and right side of the pumpkin. And if it is, then we're going to say that that's being vertically aligned with the coin. If they're not, we're going to say that it's not. And we can test that by running the code. And you can see still false. But there's a brief window where if I am vertically aligned with the coin, if I'm above or below it or on top of it, that is true. And if I go too far left or too far right, it is false. Yay. So now all I want to do is I want to check the other axis is horizontally aligned. And we're going to do it in pretty much the same way. Local top equals self.y, local bottom self.y plus self.height. Let's copy this. Is horizontally aligned. Top, bottom, y. So the top, if the x and y value of the pumpkin represent the upper left corner, then the y value is the top side of the pumpkin, which means if we want to get to the bottom side of the pumpkin, we just add the height of the pumpkin and we get the bottom edge. That's what this does. And then again, we're just checking to see if the coin's y value is between the top and the bottom of the pumpkin. And if they are, we're going to say that counts as being horizontally aligned. And then let's print out that value. Is horizontally aligned. And we'll put that below what we had before. Let's draw it in gray just to distinguish it further. So now if I am above the coin, it counts as being vertically aligned. You can see that with the top variable changing to true. If I am to the left or right of the pumpkin, you can see that counts as being horizontally aligned. And bottom, that's good. And most importantly, if I am overlapping the coin, and only if I am overlapping the coin, both of those variables are true. So now, if we want to check to see if the pumpkin is touching the coin, all we need to see is if vertically aligned and horizontally aligned are both true. If they're both true, it is touching the coin. If one or both of them are false, then it is not touching the coin. It's as simple as that. And let's do this. If self that is horizontally aligned, so let's see, collect the coin. If it is horizontally aligned and it is vertically aligned with the coin, then coin dot is collected equals true. That doesn't mean anything, so we need to do something that makes that matter with the coin. Let's add is collected equals false. It starts uncollected. And let's only draw the coin if it's not collected. So as soon as the coin becomes collected, we will stop drawing the coin. And if we go back, boop, and let's turn off all of our debug stuff and see what it looks like if I'm just a pumpkin and a coin. You can see I can kind of weasel my way around it and it doesn't count as collecting. Boop. But as soon as I get close enough, I collect the coin. Yes. Great. let's add a score. Yes. And let's initialize score to 0. And in our draw function, let's print score in the upper left-hand corner. And when we collect a coin, let's increment score. Score plus equals 1. And this is the exact same code that we use to increment the x and y value of the pumpkin to get it move around. Let's try that out. Whoops. So it looks like if my score is going up a lot, and it looks like if I just sit on where the coin is, my score keeps going up. And that's because there's nothing stopping me from collecting a coin that's already collected. So let's do that. If we collect the coin, if we're horizontally aligned with the coin, and we're vertically aligned with the coin, and the coin is not already collected. Boom. And now I can only collect the coin once, which is good. But we want more than one coin. Our game is going to have so many coins. And so we need to... I don't want to like make another coin 2, coin 3, coin 4. Because then if I wanted 100 coins in my game, that's going to be a lot of typing for me. And I don't want to do that. So let's create a variable coins. And here, where I'm saying coin equals, let's say coins equals. And let's comment this out. Boop. And here where I'm saying coin update and coin draw, let's comment those out too. When we created our pumpkin object, we created this curly brace object and have lots of parameters set on it. We have some numbers, we have some booleans, we have some functions. What I want to do is I want to make a list of coins. And a list is... Let's say that I wanted to have a list of even numbers. That would be something like this. Local even numbers equals 2, 4, 6, 8, 10, 12, 14. And if I wanted to get, I guess 0 is an even number. Yeah. And if I wanted to get like the third even number, I would just do even numbers, square brackets 3. And this would give me 1, 2, 3. This would give me 4. And if I wanted to get like the last even number I have in this list, I would just do pound even numbers, pound sign, and then a list returns the length of the list. This list is 1, 2, 3, 4, 5, 6, 7, 8 items long. So this will give me the 8th item, which is 14. If I wanted to change the list, I could do add even numbers 16 to put a new number into it. If I wanted to remove a number, I could do delete del even numbers 4 to get 4 out of that list. We don't want to work with numbers though. We want to make a list of coins. And the coins aren't just going to be numbers, they're going to be objects. So I'm going to make a new list of coins. It's going to be empty to start. And I could do something like this. Where I make a list and then I just paste a bunch of coins in there. And then we would have 5 coins. And I could change the X and the Y value of each of them. That's not the best way to do it because that's a lot of copy code. I'm a very lazy person. So we're going to do it better. What we're going to do is we're going to make a make coin function. Function make coin. What do we need to do to be able to make a coin? We need to know where to make it. So we'll need an X and Y value. And what will it do? It will make a new object. Local coin equals X equals X, Y equals Y. We need some other stuff. Let's copy it here. When we make a coin, it starts out uncollected. It has an update. It knows how to update and draw itself. This is a good make coin function. The only thing we need to do is we need to return coin. What return does is if we call make coin, let's say 50-50, This will make that object, and what will return will do is it'll give us back that object. So I could be like local coin equals make coin. What I want to do though is I want to make a list of coins. So I'm gonna make coin 1010, make coin 40 20. Let's just 90 20. I don't know what. I'm just entering random pseudo random numbers. So now we've made a list of 6 coins, assuming this make coin function works. It doesn't have any errors. Let's run our code. It does. Attempt to index global coin. Line 33. So in our pumpkin's update function, we're referring to coin, but coin no longer exists, so I'm going to comment this out for now. And we can see our pumpkin is very lonely because there are no coins here, even though we made 6 coins. Right here, we made a list of 6 coins. So why aren't they appearing? That's because we commented out the part where we drew the coin. And we commented that out because we no longer have a coin, we have many coins. And what we want to do to draw many coins is we say for coin in all coins, do coin draw. So this is known as a for loop. Basically, I'm saying I don't want to just draw a coin, I want to draw all the coins. So take all the coins, and for each of them, draw it. And now if we save that and run our code, you can see all the coins that I've created. Lovely, our pumpkin isn't so lonely. Our pumpkin can't touch those coins yet. And that's because, again, we commented out the pumpkin code where we're checking to see if the pumpkin is colliding with a coin. Let's do this though. Let's say in our update function, so let's do the same thing where we're updating all of our coins even though that doesn't do anything at this point. For all coins, call update. I think it's proper form to do local coin, since coin is a local variable there, to not leak that into global scope. So for all coins, update them. This doesn't do anything. Let's just make sure that our coins are updating properly by giving them an update function. Let's say self.x plus equals 1. Now when I run this code, all my coins should fly to the right, which they do. We don't want that though. I'm just checking to make sure we're updating our coins properly. We want to check to see if our pumpkin is colliding with any of the coins. So let's do it like this. Let's do it a proper way. Let's say for coin in all coins, update the coin, and then pumpkin, check for collision with that coin. So for each coin, we're going to update it, and then the pumpkin's going to check if it's colliding with that coin. And this function doesn't exist yet. We need to define that. Check for collision function, self coin. So this function will take in the pumpkin, take in the coin, and determine if they're colliding. And that's just this code. I'm going to take it out of the update, put it into the check for collision. And we don't need to change anything because this code was referring to coin and our variable name is still called coin. Let's check to see how this works. Boop. Great. So now my pumpkin can collect all the coins. It's beautiful. So now we have hit detection. We can detect to see if a pumpkin is colliding with coins, which is a weird sentence, but it's true. And you can see it's a little bit, because we're just checking to see if the center point of the coin is within the pumpkin, I can kind of glide by these pumpkins without collecting them. If you're curious about like why we don't just do pixel detection to see if like, oh, one of the yellow pixels of that coin is crossing over one of the orange pixels of the pumpkin, why don't we just do kind of like a visual comparison of those two sprites and see if they're colliding? There's two reasons to do that. One is you need to check every pixel in the coin against every pixel in the pumpkin to see if they're colliding, and that would be very expensive. Whereas with this technique, we're just comparing like 6 numbers, which is much easier and faster. The other thing is there are a lot of cases where you don't want pixels in the sprite to be what determines whether or not there is a hit. Like you can imagine a fighting game where maybe a character has a lot of like very big poofy hair. You might not want their hair to count as a hittable area. Maybe if someone punches their hair, the punch should just go right through it. Let's abstract away a lot of this code. Let's make a function. Function is point in rect. And I'm going to make this function, and it's going to take in a point x, point y. Well, let's take an x and a y. Let's take a left, a top, a right, a bottom. And what this function is going to do is it's going to compare those numbers and determine whether or not the xy point is within the rectangle defined by that left, top, right, bottom. So how that function's going to work is we're given the top and bottom, we don't need that. We're given the left and right, we don't need that. We don't have a concept of a coin, so we can just take away that, and instead we'll just be using the x and y value, which is good. We don't care about this coin collected stuff, since that's a concept of coins, and we're just talking about rectangles right now. And we're not going to want to increment the score. They are colliding. Let's say local is horizontally aligned, local is vertically aligned, and then no concept of self. If is horizontally aligned and is vertically aligned, then return true, else return false. So this code works. This checks to see if a point is within a rect. You give it an x and a y position, you give it a left, top, right, bottom, that is the rectangle, and it will tell you whether or not a point is within a rectangle. And we can, we can verify this by going back up here. We're going to get the top and bottom, we're going to get the left and right, and instead of doing this, we're just going to call if is point in rect. The point we want is the coin's x and y position. The rectangle we want is the pumpkin's rectangle, which is left, top, right, bottom. And not coin is collected, then the coin is collected and score increments by 1. Ran the code with Control R. There's an error. Unexpected symbol near blah. There's a little period here. Ran the code, it's still working. It's still properly collecting coins, but we can do better. So this is looking a lot better. You can kind of see more what it's doing. It's when we're checking for a collision with a coin, we're just checking to see if the coin's point is within the pumpkin's bounding rectangle and the coin's not already collected. So it's a lot easier to read. So we already have one benefit of moving this out into its own function. What I'm going to do now is let's clean this up, because we can clean this up a ton. So the first step is we're setting is horizontally aligned to true only if top is less than y and y is less than bottom. One shorthand, and otherwise we're setting it to false. A shorthand we can do is we can just set is horizontally aligned to that value, which will be either true or false. That's how this if works. This will evaluate to true, and then is horizontally aligned will be set to true. If this evaluates to false, then it will be set to false. Why not instead just take what this evaluates to and set that variable to it? Same thing here. Is vertically aligned just equals this. If it is horizontally aligned and is vertically aligned, if this statement evaluates to true, we're going to return true. If it evaluates to false, we're going to return false. Why not just return? this. Bum, bum, bum. That seems a lot easier to understand, or at least cleaner in terms of code, and it saves us a lot of tokens of code, and PICO-8 is super token restricted, so that's better. Let's do even one step better. Is horizontally aligned is just this. Why not just check to see if that and that, boom, and these parentheses are actually superfluous because we're just doing a bunch of ands. So this is the code you end up with to check to see if a point is within a rectangle, and it's very simple in the end. You just check to see if the y value is between the top and bottom, and check to see if the x value is between the left and right of the rectangle. And that's all you do to check to see if a point is within a rectangle. Very simple code, actually. And we can see it still properly detects whether or not my pumpkin is detecting coins. Or is colliding with coins, rather. Yes. So there's a lot of times in games when you're not just checking to see if a point is within a rectangle, you're checking to see if two rectangles are overlapping. Like in fighting games, a character isn't a point, they are a big old box. And if your punch box is overlapping with their torso box, that counts as a hit. So checking to see if rectangles are overlapping is actually a much, much more robust way of doing hit detection. So we're drawing our pumpkin's bounding box again. Let's give our coins in the make coin function, let's give them a width and a height. Height 8. And let's also draw their bounding box. Self.x, self.y, self.x plus self.width, self.y plus self.height. Now let's draw a blue rectangle around them. So we keep switching between whether or not the coin's x value represents its center point or its upper left point. If we're going to do a bounding box like this, it would be easier for us if the xy value represented their upper left point, which means shifting that sprite up and to the left is misleading now. And actually, width equals 8, height equals 8 is also a little bit misleading too. Let's change our width to 6 and our height to 7. Let's see if that, there we go. That hugs the bounding box of the coin a lot better. So now our coins have a concept of width and height, and I don't want to check to see if a coin is within a rectangle just by checking the point. I want to see if the coin's rectangles are overlapping with the pumpkin's rectangle. We need an algorithm that detects whether two rectangles are overlapping, and it's actually a lot similar to what we just did. So if I have these two rectangles, and just imagine that the red and blue projections coming off of them, we're going to be looking over here at them. So let's look over here. This is actually a very similar situation to what we had before, where if we want to check to see if two rectangles are overlapping, we're going to look at each of their axes independently. So to start with, we want to see if this little red area over here is intersecting with this little blue area over here, which it's not currently. But if we moved it down, then now they are overlapping a little bit. But if we were to look at their vertical projections, we can see that this red area over here is not overlapping with this vertical projection of the blue area over here. So they're not overlapping, and if we move them a little bit closer, we see they would be overlapping. And if it's the case where the projection onto a horizontal axis, if they're overlapping, and the projection onto a vertical axis, if they're overlapping at all, it must be true that the rectangles themselves are overlapping. There's no way for them to not be overlapping if their two projections are. And if one of them isn't overlapping, like here, if the horizontal projection, there's a little gap between it, there's no way for the rectangles to be touching each other. We want a way to check to see if this is overlapping with this, mathematically. We could again consider that this, because we're talking about a horizontal axis, the beginning of this blue area has an x value, the beginning of this blue area has an x value, same thing with this and this red area. And if we were looking at the projection onto a vertical axis, we would have a y value for this start of red area, the end of the red area, the start of the blue area, and the end of the blue area. So we're going to be talking about the x and y values again. So what are all the ways that two horizontal line segments could have relation to each other? It could be the case that the blue one is to the right of the red one. They're not overlapping at all. Or it could be the opposite case, where the blue one is to the left of the red one and they're not overlapping at all. Or it could be the case that they're overlapping like this. Or it could be the case that they're overlapping like this. It could be the case that the red area is contained entirely within the blue line segment, or the other way around. The blue area is contained entirely within the red line segment. So these are all the ways that they could kind of relate to each other, these two line segments. These two are situations where the line segments are not overlapping at all in the horizontal axis. Well, these are the ways in which they could be overlapping. In this case, we can see that the blue's right side is greater than the red's left side, and they're overlapping. But we can also see that's true here. Whoops. We're over here. We can see that's true over here too, where the blue's right side is greater than the red's left side. So this alone, if this property is true, if the blue's right is greater than the red's left, that doesn't necessarily mean that they're colliding. But there's one other thing we can look at, where we can look at the red's right and the blue's left. Whenever they're overlapping, it's the case that, first off, one of the sides of a rectangle is between the two sides of another. So in this case, the blue's right side is between the red's left and right. In this case, it's the opposite. The red's right side is between the blue's left and right side. And it's true over here where the red's left side is between the blue's side, and over here the blue's left side is between the red's sides. Here's a special case where both red sides are between the blue sides, and the opposite, both blue sides are between the red sides. And here we can see that there is not that property, where there is no side. The red sides, neither of the red sides are between the blue sides, neither of the blue sides are between the red sides in either of these cases. So this is the property we can use to check to see if these two line segments are overlapping. Let's just code that up right now and we'll come up with an even better algorithm in a second. Function lines overlapping. Left one, right one, left two, right two. So this is red's left, this is red's right, left one, right one, this is blue's left, this is blue's right, left two, right two. That's the way we'll do it. And if we want to see if two lines are overlapping, two line segments on the same axes, we'll just check if, let's check to see if this is between these two segments, or this is between these two segments, or this is between these two segments. So let's just iterate through them. So if the left side of one, so let's consider this left side of the red, is between the two sides of another, is between left two is less than left one, and left one is less than right two, then they are overlapping. And we can do the same thing with, let's check to see if the red segment's right side is between them, which is right here, then they're also overlapping. And we're going to just check right one. And we're going to do the same thing for if, let's look at this blue's left side, which we'll say is left two. If left two is between left one and right one, then they are overlapping. So left 1 is less than left 2, and left 2 is less than right 1. Then return true. And we're going to do the same thing for right 2. And then if none of those are true, we're going to return false. And let's do some else. Else. There we go. If none of those are true, return false. So this is an algorithm to determine if two lines are overlapping. Two lines along the same axis. Two line segments along the same axis are overlapping. Which is great, and that should work just fine. I believe there is a simpler algorithm though, where there is a property where if blue's right is greater than red's left, and red's right is greater than blue's left, then they are overlapping. And that's a much simpler condition. So let's compare. So in this case, we're comparing the blacks and the reds. So blue's right is greater than red's left. And when I say greater than, I mean more towards the right side of the screen. Maybe it's this way on the screen. I don't know. In this case, blue's right is greater than red's left. Blue's right is greater than red's left. Blue's right is greater than red's left. So it's true for all of these. Blue's right is greater than red's left. It's true for this one too, though. Blue's right is not greater than red's left. So that's not true for this. And that's why they're not overlapping. And we'll do the same thing where they're overlapping if red's right is greater than blue's left. 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 So it's true for all these that red's right is greater than blue's left. And if we were to do it here, red's right is not greater than blue's left. And in here, this case, red's right is greater than blue's left. So if we just look at those two conditions, that red's right is greater than blue's left and blue's right is greater than red's left, these two conditions fail those statements, whereas these all succeeded those statements. So that's a simpler way to do this check. Where we're going to, this will work just fine, but we want to check to see if right 1 is greater than left 2 and left, let's get this right. Blue's right, let's say that red is 1 and blue is 2. Red is 1, so if right 1 is greater than left 2. Right 1 is greater than left 2. And right 2 is greater than left 1. Right 2 is greater than left 1. Then they are overlapping. Otherwise, they're not. And all this code we just wrote, this is a simpler way to do it. Hooray! And much like how we simplified this isPoint in Rekt function, we can simplify this too, where we can just do return right 1 is greater than left 2, and right 2 is greater than left 1. And that's the only code you need to check to see if two lines along the same axis are overlapping. That's it. We can actually delete this, even though it would have worked. Now, if we want to check to see if two rectangles are overlapping, and let's imagine that what we're passing in is we're passing in a top or a left one, top one, right 1, bottom 1, left 2, and then we're passing in. So we're passing in the left, top, right, bottom of a rectangle, and then the left, right, top, bottom of another rectangle, and we want to see if they're overlapping. What we'll do is we're going to check to see if the lines are overlapping. Left 1, right 1, left 2, right 2. So if the lines are overlapping on the horizontal axis, and the lines are overlapping on the vertical axis too, which would be top 1, bottom 1, top 2, bottom 2, then two rectangles are overlapping. Otherwise, they're not. Which again, we can just say return this. And that's the code for doing rectangle-based hit detection to see if two rectangles are overlapping. Let's make sure this works by putting it to the test. These are a little bit misleading. Let's call these min and max, because it's not specifically horizontal, it's horizontal and vertical axes that this can test for. Great. Let's check to see if, so let's change our pumpkin. So it's still checking to see if it's colliding with things by using the center point of the coin, which is misleading. Let's check for collisions using this. So these are the pumpkin top, pumpkin bottom, pumpkin left, pumpkin right. Let's get also the coins, coin top, and we'll just do that by setting. So we're going to get the coins top, bottom, left, right. To check for a collision, we're just going to do, let's check this first. If the coin is not already collected and Rek's overlapping, we're going to pass in all these. Let's add some commas. Pass in all those parameters. Pumpkin, top, bottom, left, right. These are out of order. Left, pumpkin top, pumpkin right, pumpkin bottom. Coin left, coin top, coin right, coin bottom. Let's run it. And let's hope that it works. Yes. Boom. Boom. I'm just trying to approach these coins from different angles. Boom. Great. So now we're properly detecting, are the bounding boxes of the coins colliding with the bounding box of the pumpkin. And this is a little bit better because we can, we don't need to be overlapping with the center point of the coin. We just need to be overlapping somewhat with the coin. Let's get rid of these bounding boxes. We don't need to draw them. They don't do anything when we draw them. Let's see what it looks like there. Boing, boing. We're collecting coins. Great. Let's review one other means of doing collision detection. And I like this one because it's also very quick. It's actually a lot simpler to understand, which is why I like it. And it has a lot of applications. You might even prefer in some cases to this type of collision detection. And what I'm going to do is we're going to do circle-based collision detection. So if I wanted to see if these two circles were overlapping, what I could do is so let's say they're overlapping right now, they're still overlapping, but if I move it like this, they're no longer overlapping. An algorithm we can use is we can compare the distance between the center points of these circles, and if the distance between those center points is less than the sum of their radii, which would be the sum of these two, then they are overlapping. And to kind of give a sense of that, let's just draw their radii right here, and let's move these down here. Well, what am I doing wrong with these? I keep screwing this up. Well, let's put them on top of each other. Oop. So this is the length of the sum of their radii. And if I were to, if I were to put these circles like this, and I were to draw a line from the center point of one to the center point of the other, it would be like this, which you can see is shorter than the sum of their radii, and they are overlapping. So in this case, the distance between the circles is smaller than the sum of their radii, and they are overlapping. If I were to move this red circle further away, and draw a line between their center points, you can see that this is, whoops, the distance between their center points now is greater than the sum of their radii. It's longer than it. So a very simple algorithm is if the distance between the center points of two circles is greater than the sum of their radii, then they're not colliding. Otherwise, they are. Our pumpkin and coins don't have a concept of radius at this point, so let's add a radius to them. Let's say our pumpkin's radius is 6, and if we want to see what that looks like, we're going to self.x, self.y, self.radius 7. So we're now, before we had a bounding rectangle, now we're going to have a bounding circle around our pumpkin. And you can see we're getting into the thing again of like, does our x and y value represent the center point of the pumpkin, or does it represent the upper left corner of the pumpkin? And if we're going to use a circle for our hit detection, it would be a lot simpler if x and y represented the center point of the pumpkin. So I'm going to move the pumpkin sprite up so it's more in the center of the sprite. There we go. And now you can see I have a little bounding circle around my pumpkin, which will be what it uses for hit detection. Let's make that smaller, a little more snug. Okay, great. Let's do the same thing for our coin. Coin equals radius equals 5. We're going to need to do the same thing. That radius looks too big for the coin. Let's make it a little bit smaller. Let's make it blue again. Doop. And so now all of our objects have bounding circles around them that we're going to use for hit detection. Function check circles overlapping. And now we're going to write a function that checks to see if two circles are overlapping. So what we'll need is we'll need an x1, a y1, and a radius, an x2, a y2, the position of the second object and the radius of the second object. And that's all we need to check to see if two circles are overlapping. And it's very simple. The distance between two points in a Euclidean plane, we just look at the distance between their x values and the distance between their y values. And if we wanted to get the distance, the total distance, we take the square root of dx times dx plus dy times dy. And that's the distance between them. And if dist is less than r1 plus r2, if the distance between them is less than the sum of their radii, then return true, else return false. This is again one of those situations where why don't I just return dist less than r1 plus r2? So I will. And that's all you do to check to see if two circles are overlapping. And now I have this code for checking between a collision between a coin and a pumpkin. And let's just comment that out. Let's check to see if circles overlapping. And I'm just going to check to see if pumpkin.x, pumpkin.y, pumpkin. Oh no, sorry, self.y, self.x, self.x, self.y, self.radius. So check to see if two circles are overlapping. The first circle is the pumpkin's bounding circle. The second circle is the coin's bounding circle. And if those circles are overlapping, we're going to count it as the pumpkin collecting a coin. And so now you can see that this type of hit detection is working. Boop, 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 boop. And maybe it would be easier to see if I increase the radius of each of these. Let's do this. Radius equals, let's do 3 times. So I made the radii even bigger, and now it's a little bit easier to see that the pumpkin's moving around, it's not collecting the coin, but if these two circles overlap, then it does count as collecting them. Boop, boop. Yes. One thing to consider with this is SQRT, square root. You might remember that from math class. That's actually a little bit of an expensive function. Not really that much, but notable enough. So we might want to check, instead of multiplying is a very cheap operation, whereas taking the square root of something is a little more expensive. What might be easier is, let's check to see if dx times dx plus dy times dy is less than r1 plus r2 times r1 plus r2. Then, and this is, you can kind of see that I'm taking the square root of this same expression. And in a way, r1 plus r2 is sort of like the square root of this expression. So I'm actually comparing the same thing, just squared. And if this is true, then they are overlapping. So this is sort of like the same comparison, except we don't need to use the square root. The downside is we don't know the distance between the points, but we actually don't care about what the exact distance is. We just want to make sure that it's not greater than the sum of the radii, which is the same as saying don't let the square distance be greater than the square sum of the radii. So saves a little bit on performance, and same code. One thing that might trip you up here is if I move the pumpkin all the way down. I wonder if this will happen. Yep, if I move it down to the right, we'll start collecting all the coins on the screen. Why is that, you may ask? Good question, I might say. As I move my pumpkin over here, the distance between the pumpkin and that coin in the upper left is getting bigger and bigger. And it's getting to be the point where it's about, let's say it's about 150 pixels in the dx axis. And let's say dy is also around 150. And if we were to look at this expression, dx times dx plus dy times dy, if we were to plug in 150 for each of those and see what that is, it's a pretty big number, 45,000. The maximum integer that PICO-8 can handle is somewhere around 32,000. And if you try to play with an integer that's bigger than that, it'll wrap down to negative 32,000. So what's happening here is the pumpkin is getting so far away from the coin that integer overflow is triggering, and our distance calculation, dx times dx plus dy times dy, is becoming a very big negative number, which our computer is interpreting as, oh, they're really, really close. Like so close, they're negative distance close, which isn't really possible. So to protect ourselves from this, we just need to make sure dx and dy don't get too big. A way to do that is there's a function mid that you give it 3 parameters and it'll return the number that's in the middle, the middlemost of those 3 parameters. So let's say x2 and x1, let's say that was like 500 pixels, or yeah, 500 pixels. If I were to do mid negative 100, 500, 100, the middlemost number in there would be 100. So then therefore dx would be 100. And if I were to try 100 times 100 plus 100 times 100, this expression is now under PICO-8's maximum integer overflow. So now, if I were to move my pumpkin down and to the right, integer overflow will not trigger because dx and dy cannot be greater than or less than 100 or negative 100. So there's 4 different forms of hit detection, and which one you choose depends on the circumstances you're in, what kind of objects you're using, how fast you need them to be, what they're going to do when they collide. There's one more type of hit detection that's significant, which is ray casting. We're not going to do that here. It's more useful in a 3D space anyway, so we don't really need to do that right now. Let's just hide the circles though. We got through hit detection today, which is a big topic. That's really great. Hit detection is a super important part of like making a game. I'm going to end it there. You can also message me on Twitter, or if you're watching on YouTube, leave a message in the comments below. But thanks so much for watching, and if you can make it tomorrow or on Thursday at 2 p.m., I look forward to seeing you all there. So, have a good day!